Good afternoon to everyone, and glad to be able to continue the series. Sorry for the 2-week hiatus, but my schedule was booked up the last two weeks. So today we have a topic on seismic reflections, and this is something that is fairly basic for those of you who are geophysics specialists. But we probably have a number of people listening in or watching that maybe are more geological or geochemical, and the geophysics is something they struggle with a little bit, which is fine. I've struggled with it for 40 years. So the ideal seismic response is one that would allow us to resolve beds that are only a few meters thick. There's an outcrop photo here from West Texas. You can see two people for scale, and you can see the layering in the rocks. And if we had ideal seismic, we'd be able to see reflections associated with the boundaries between the different rock units. And so there's a 1 meter scale bar on the upper left. And so the individual blacks, which are increases in impedance, or the reds, the decreases in impedance, are such that we're able to see the tops and bases of some of these bedding units. But unfortunately, we don't have the ideal world. In terms of stratigraphy, there is a hierarchy that many people are adhering to. They go from very small, thin units with very limited extent, lamina and lamina sets, and it builds up into much larger, widespread, thicker units, more geological time represented, sequences and sequence sets. And the hierarchy is such that lamina build up lamina sets, several lamina sets build up beds, several beds build up bed sets, and so on and so on and so on and so on. There's some terminology that people that work this type of stratigraphy have developed. A depositional sequence is considered a third order unit, and a sequence typically has a geological span or range of ages of 3 to 5 million years. As we go to larger scale units, the number goes down, so sequence sets, a stack of several related depositional sequences, is considered second order. And then from the sequences, if we go to smaller scale, the parasequence set would be fourth order, and the parasequence fifth, and so on and so on and so on. If we're looking at core data, typically what we would be looking at are lamina sets, beds, and maybe up into the bed set stage. If we're looking at logs, we can't see the lamina sets unless we have image logs. With most of the wireline logs, we're looking at beds and bed sets and parasequences, parasequence sets. With seismic, we can't see the really small stradal units or stradal divisions, but we can see parasequence sets, sequences, and sequence sets. Of course, seismic resolution is going to vary the bandwidth of the seismic and how deep we are in the subsurface. So for seismic data, the resolution is somewhat limited, and we see units that are on the order of maybe 20 to 30 meters thick. But the advantage of the seismic is that we can get a large aerial extent in terms of coverage. If I had a map up of the Gulf of Mexico, the U.S. Margin, and threw a dart at it, almost every place that the dart would fall, we would have at least a 2D survey, and probably 80% of the U.S. Gulf Coast is covered by 3D seismic survey these days. So the real pulse is much less precise, much lower resolution than on the second slide, I think it was, where I talked about the ideal response. So here we have another outcrop. There's a scale bar in the lower left of 5 meters. And the lighter units here are predominantly sand. The darker units below it and above it are primarily shale. And so with modern day seismic, looking at things that are not extremely deep, we might be able to pick out packages of sands and packages of shales, not individual beds or bed sets. Let me talk a little bit about some of the lingo that we use when we talk about seismic waves. We have a trace here. 0 would be no response. And then we can get negative numbers on our seismic trace or the tape of the values. We can get positive numbers. And different people have different ways of representing negatives and positives. In most cases, negatives would mean a rarefaction and a positive would be a compression. So 0 to the positive numbers would give us what we call a peak. 0 to negative numbers is what would give us a trough. One of the main seismic attributes people worry about is seismic amplitude, and that's what's the deviation from 0. So how positive is the peak, what's its maximum number, or alternatively, how negative is a trough, what's the maximum negative number. We also talk about the wavelength. How long in feet or in meters does it take for a wave to develop and pass? We also talk about the period. That would be the time that it takes for a waveform to pass a given reference point. And we measure that in time, or more commonly in millions of seconds, milliseconds. And the other thing that we talk about is pulse duration. And it's very similar to the period. How long does it take for the pulse to show its full sinusoidal type shape? There's a couple of basic equations. Equation 1, the period is 1 divided by the frequency. That's a commonly used equation. Equation 2, the wavelength, that's the velocity times the period. And I can substitute from equation 1 for the period and say the wavelength is the velocity divided by the frequency. And D in this case is depth. It's the velocity times T is two-way travel time. And we divide two-way travel time by 2 to get one-way travel time. So those are probably the 3 basic equations in terms of understanding and describing the different waveforms of the seismic pulses. A very basic question is what causes seismic reflections? And a reflection is caused when there's an interface between bodies or layers that have different acoustic properties. We define a term called impedance, and usually represented by a capital I, although I know some people use a capital Z or Z. Impedance is defined to be the velocity of the rock times the density of the rock. And so the interfaces between layer 1 and layer 2, for example, that boundary separates rock of one impedance from rock of a different impedance. If the impedance change is small, that would lead to a small amplitude reflection. If the impedance change is large, that leads to a large impedance reflection. So here we have an example of an interface. We have shale sitting on top of sand. The shale has a velocity of 2,300 meters per second and density 1.8. The sand, slightly higher velocity, a slightly lower density. There's an equation, a reflection coefficient equation. The reflection coefficient is the impedance below minus the impedance above the boundary divided by the sum of the impedance below plus the impedance above. And so we can use this, and the reflection coefficient tells me how much of the energy reaching that interface would be reflected back up towards the surface. So I can figure out for the shale, the impedance is 2,300 times 1.8, so it's 4,140 units. We won't worry about all the meters and grams and cc's. For the sand, the impedance is 2,450 times 1.7, or 4,165. And then the reflection coefficient, I can take the impedance of the sand minus the impedance of the shale divided by the impedance of the sand plus the impedance of the shale, and that gives me a reflection coefficient of 0.003. So that would say that of the energy that reaches that interface, only 0.3% of it is reflected, and the rest of it would be transmitted to deeper and deeper layers. It's fortunate for us that reflection coefficients typically are less than 1%, because that allows us to have energy go down to depths of 10,000, 20,000, 30,000 feet to regions in the subsurface where we might have oil and gas. Oh, my advance is not there. Okay. So we have at the surface a source of energy, and I'll talk more about that a little later. We'll have receivers. And so we will have a shot go off or a vibrator truck vibrate. Some energy goes down, hits the first boundary. Part of it is reflected back, a small percentage, most of it is transmitted. I have the listening device. It starts at 0 with no disturbance. And then at a certain time, I get, in this case, a peak followed by a trough. And depending on how I have set up my parameters, for me, a peak followed by a trough indicates that it's an increase in impedance. At the same time that the blue ray path is occurring, we can have the red ray path where energy goes down, transmitted through the first interface, is reflected off of the second, comes back up, and it is received. And instead of coming in at 0.65 seconds, that comes in at 1.4 seconds, and those would be in units of two-way travel time. So we can think of the Earth as an acoustic structure with different layers of impedance, and that, again, impedance of the first layer is the density of the first layer times the velocity, and the second, the third, the fourth. I can show that impedance structure as a log with increases in impedance for the first two boundaries, a slight decrease, and then a major increase for the fourth boundary. I can use the equation that was on the previous slide, impedance below minus impedance above divided by impedance below plus impedance above, and calculate reflection coefficients. Spikes to the right indicate a positive reflection coefficient or an increase in impedance, such as here and here, giving positive responses. The magnitude of the spike tells me how big the impedance change is. So larger impedance change here, moderate here, larger and moderate. If I have layer 3 has higher impedance than layer 4, then the reflection coefficient is a negative number, and a negative reflection coefficient tells me it's a drop of impedance. The magnitude is moderate, and then I have a large increase in impedance, so I get a large positive spike. If I know the waveform or the pulse that I send down into the Earth, I can use a mathematical operation called convolution to take this pulse and convolve it with this reflection coefficient to get this peak and trough, with this pulse to get this peak and trough. Since this is a negative reflection coefficient, it's the mirror image, so it's a trough followed by a peak. And then the large positive gives me this large peak followed by a large trough. And so at a particular location, the receiver is hearing that information simultaneously, and it will display positive numbers, negative numbers as a function of two-way travel time. So the pulse can be pesky. If the frequency content or the bandwidth is very large, then the pulse approaches that idealized spike, and we'd be able to resolve fine-scale stratigraphy. So with a very short duration, very large amplitude impulse pulse, then the reflections would mark the interfaces quite clearly. Unfortunately, with modern seismic, we typically have a bandwidth of 10 to 50 hertz, maybe sometimes 8 to 60. The bandwidth is the difference, so 50 minus 10 is the 40, and that's going to limit our vertical resolution. So instead of having a very short duration pulse, we have a longer duration pulse. And as we convolve that pulse with our reflection coefficients, we get peaks followed by troughs, or troughs followed by peaks that have a finite amount of two-way travel time associated with them. There are two types of pulses that we deal with in industry. The first is called minimum phase. These are causal. These are things that actually happen in Mother Nature. If you think about earthquake waves, those are minimum phase. Here is an increase in impedance as we go from a shale into a sand, positive reflection coefficient. We see the onset of a peak followed by a trough. And so that's the characteristic for minimum phase. The peak will be a little larger in area than the trough, so we call it front-loaded. The actual peak, the arrival time, is dependent on the frequency, and the reflection coefficient is where the energy onset begins, the zero crossing, and the peak is a quarter of a wavelength deeper than where the actual reflection coefficient is located. So there's some aspects about this minimum phase pulse that myself as an interpreter wish we could change. And because of data processing, we can change that. Most interpreters prefer to have what we call a zero phase pulse. So again, here's a positive reflection coefficient. And now we see that we have a symmetric pulse. We have a little bit of a peak followed by a major, a little bit of a trough followed by a major peak followed by a little bit of a trough. We call the first trough a precursor and the second one a postcursor. The wavelet is symmetric about the reflection coefficient, and the maximum amplitude is coincident with the depth of the reflection coefficient. So it is symmetric. The maximum, the peak arrival time is not dependent on the frequencies that we have. The maximum peak to side lobe ratio is obtained when we have zero phase, and the reflection coefficient is at the maximum displacement, whether that's a peak, in this case for a positive reflection coefficient, or if we had a decrease in impedance, a negative reflection coefficient, it would be centered on the most negative number within the trough. So I mentioned polarity, and polarity is how we will see an increase in impedance. We have SEG is the Society of Exploration Geophysics. They have a normal convention. So if we have a minimum phase pulse or minimum phase data, then negative numbers on the tape would be a compression, and they would be displayed as a trough. So for an increase in impedance, we would see a trough followed by a peak. If, however, we have a zero phase, SEG normal for that is that a compression, an increase in impedance, a positive reflection coefficient, would be represented by positive numbers on the tape, and it would be displayed as a central peak with a little bit of side lobe energy before and after. So if we have a single interface, like I talked about before, shale sitting on top of sand, if in this case the shale is lower impedance and we have a step up to a higher impedance shale, it would generate a positive reflection coefficient, and the zero phase response SEG normal convention would be to have a central peak with a little bit of energy as a precursor, a little bit of energy as a postcursor. We can use a mathematical operation called convolution to convolve the pulse that we are sending down with the reflection coefficient to get what the modeled seismic response would be. If we have more than one reflection coefficient, here we have a shale, a thicker sand unit, and a shale. The top of the sand is an increase in impedance, so it's a positive reflection coefficient. The base of the sand is a decrease in impedance, so it's a negative. And if we have a zero phase pulse, we have a peak marking the top of the sand, we have a trough marking the base of the sand. We consider this a thick interval if the response from the top of the sand finishes or completes before the response at the base of the sand begins. And so if the sand unit here is thick enough, we won't have difficulty in picking both the top and the base. But what happens if the unit gets thinner? The interference, the response for the top of the interface does not finish before the response of the base begins. And that way we start to have what is called interference. So the two responses will coexist, the two values get added together, and so the receiver is not able to distinguish what the tail response to the top of the bed is versus the start of the response from the base of the bed. And so if we have two reflection coefficients fairly close together, we have a peak associated with the increase in impedance at the top, a trough associated with the decrease in impedance at the base. We add those two together and we can get constructive interference. This peak is larger than either the red peak or the magenta peak because those two positive numbers are going to add. Similarly, on the composite, the trough negative numbers are greater than the negative numbers for the magenta or for the red. The other thing that we could have is two reflectors close together that perhaps have the same polarity. And so the response for the first reflection coefficient is that peak. For the second is that peak. We add the green curve and the blue curve together and we get a composite, and we don't see clearly defined peak associated with either of them because of destructive interference. So with seismic data, we see reflections that tend to parallel the mid to lower order stradal surfaces, the para-sequence sets, the sequences, and the sequence sets. Reflection terminations mark where we have unconformities, and we'll talk more about that when we get to seismic stratigraphy in a future lesson. And changes in reflection character along a reflector is what tells me something about facies changes. So this blue line here, it starts up dip in coastal plain. It goes through the green, the foreshore. It goes through the tan, the lower shore face, and then into the slope basin. And so up here, a reflector would have low amplitude because we have very similar rocks, very similar velocities and densities, very small changes in impedance. When we start to interfinger one lithofacies with another, one color with another, we have a chance for higher impedance contrasts. And then it would get to be very low when we're out in the basin and we have shale sitting on top of shale. Again, the velocity and density changes would be very small, and so we get small amplitude responses. So why do reflectors follow stradal surfaces? As I mentioned, impedance is equal to the velocity times the density. If we consider where we have sharp changes in impedance, we can think about how those changes might occur horizontally and how they might also occur vertically. So here's a picture of an outcrop. This is from West Texas. The scale here, the black bar is 365 meters or 1,200 feet. So quite a thick unit here. We have at the very base, the Pipeline Shale. Then we have above that the Lower Brushy Canyon Formation, the Middle Brushy Canyon, and the Upper Brushy Canyon Formation. So the Pipeline Shale is a basinal shale, and as we go from lower to middle to upper brushy, we go from lower continental slope to mid-continental slope to upper continental slope. We have more shale in the lower brushy. We start to get more sands in the middle brushy and even more sands in the upper brushy. On the outcrop, the whiter units, this is a thick one right here, are the sands, and the darker units are the shales. So we can go to this location in West Texas and get actually on this layer with the thick white, and walk that out for several miles. And if we were to look at physical properties, let me back that one off, along one of these layer boundaries, let's say we're looking at this unit here. In this location, maybe it's 60% sand. We go a quarter of a mile, maybe it's 58%. We go a little more, it's maybe 55%. Go a little more, maybe it's 52%. Left is landward and right is basinward. So the changes in the rock properties and therefore in the impedance are very gradational. However, if we got a summer intern and asked the intern to go down the slope and sample the rocks, let's say every meter, the first sample where the little green arrow is, that might be 60% sand, and then it's a silt, and then it's a shale, another shale, a silt, a shale, a sand, et cetera, et cetera, et cetera. So we would see more changes vertically in physical properties than laterally. And when we get to boundaries between parasequences or parasequence sets, some of the higher order depositional packages, that's where we would see the more significant changes in impedance, either increasing or decreasing. And so the reflectors tend to follow the higher order Stradal boundaries, the parasequence set boundaries, the parasequence boundaries, and the bed set boundaries, and they do not change significant, or they do not follow the changes in lithofacies, as those are very gradational and not really physical surfaces. Not every reflection we see on seismic is related to the strata. We can also see evidence of different fluid contexts. So we have a gas sitting on top of an oil sitting on top of water. In certain instances, we can see reflections associated with the change from gas to oil, and we can also see changes as we go from an oil-filled sand to a water-filled sand. We can also, on occasion, see reflections associated with fault planes. And then there are things that are non-geologic, such as seismic multiples, and various other things that could cause us to have reflections, peaks, and troughs on our seismic data. So that concludes my prepared statements for the seismic reflections lecture. Looking ahead, on Thursday, we'll start to talk about some of the risk elements, the key elements to have success. Thursday, we'll talk about source rocks, and then next week on Tuesday, we'll talk about reservoirs. Next Thursday, we'll talk about structure and traps. And then 2 weeks from today, I believe it is, we'll talk about seal and migration. Then we'll get back into some more of the geophysics and seismic interpretation. So with that, I'll stop here, and we have plenty of time to have questions.
Thank you, Fred. We have a question that just came in from Patrick Taylor. He asks, how do you generate a zero phase pulse?
In the field, most of the data is created minimum phase, but the seismic data processors can do a transformation and turn it into a zero phase pulse. So they use a Fourier transform in order to accomplish that. And on many of the interpretation platforms, whether workstation or PC based, there are tools that an interpreter can do that type of thing and on a limited basis to see how the seismic line that they're looking at might change in appearance if they go from zero phase to minimum phase or vice versa.
And it's usually instrument dependent, right? That how you would think about changing that. One of the questions is, how do you identify the tuning effect on seismic?
The tuning effect is when the interference is such that you get a maximum of constructive interference. And so one of the things you could do is you could you could interpret a horizon and then extract the amplitude and see if the amplitude is fairly constant where the bed is relative, or the unit is relatively thick, and then if it increases 50% or more in a certain region before it goes to zero. And there are tools, again, on workstation and PC interpretation platforms that if you suspect you have tuning thickness, that it can detune the amplitude map for you.
Great. Somebody asks, are you going to talk about convolution in future sessions? Are you going to go into that more deeply?
I don't think I will. I think I talked a little bit of convolution today, and I think I talked about it perhaps in session 5.
Sounds good. Alex Owen asks, can you derive porosity from acoustic impedance?
There are certain data sets in which we can use seismic attributes to derive porosity. We cannot easily derive permeability, which is the other main component of reservoir quality. So there are ways, kind of more advanced processing that can be done to try to do seismic inversion. I think I talk about that a little bit in Unit 29. And we would need some well data with porosity information in order to calibrate the seismic response. But there are a number of case studies I'm aware of where they have been successful in using different seismic attributes to get to porosity. If you then want to use a relationship between porosity and permeability, you can use that, but it's not it's kind of a second derivative from the seismic. Seismic itself is, we don't have a method to get to permeability directly.
It's true. What wavelet is best to use for wells to seismic ties? Zero phase or minimum phase?
Good question. We'll talk about well seismic ties in Unit 15. Most people prefer to use zero phase. It has a lot of nice properties, and one of which is that vertical resolution is maximized when you have zero phase data.
Great, thank you. There's a question on, can you go over how you identify an unconformity on a seismic trace?
Yes, to identify an unconformity on seismic, what we look for is a series of seismic reflections, peaks and or troughs that terminate against a common reflector. We'll talk more about that when we get into seismic sequences, Unit 21. People talk about onlapping reflectors, downlapping reflectors, erosional truncation, and toplapping reflectors. And that's the main criteria that we use, the discordance of reflectors and the systematic termination of 3 or 4 reflections to give us confidence that it's showing us a break in deposition.
Sounds good. All right, Fred, that's the end of the questions. So thank you so much for today's webinar, and we look forward to having you back on Thursday to talk about source rocks.
Okay, well, thank you all for tuning in, and appreciate this opportunity to share with you.
Great, thank you, Fred. Okay. Bye, everyone. Have a good afternoon.